Hello, everybody. My name is Ben Cline, and I'm a senior with the Math, Science, and Technology program at Paul Lawrence Dunbar High School, otherwise known as MSTC. And I've been doing research for the last year and a half at the University of Kentucky, where I've actually accumulated over 360 hours of research. So today I'm going to be presenting my research and talk about my recordings and results and conclusions I've been able to derive based off my research. And the title of my presentation is High-Speed Visualization and Analysis of Explosive Evaporation Waves. But before I get too far into my research, I'm going to give you guys an overview about what I'm going to be talking about. I'm going to start out by giving you the background and introduction information about my project to help you better understand this before going too far into the project. And then I'm going to be proposing my research question of what I was trying to address with my experiment and the initial hypothesis I had at first. And after that, I'll be talking about the methodology I did to conduct this experiment, the results and analysis I found by doing the methodology, and the conclusion I've been able to derive based off my results. And after that, I'm going to be talking about further research on how this project can be expanded upon in the future and also be improved upon, as well as applying to the real world. And after that, I'm going to be concluding by having some acknowledgements, references, and questions. And before I get too far, I'm going to give you guys some definitions. I'm going to start by defining what is an evaporation wave. An evaporation wave is a moving interface between a superheated liquid and its surrounding gas. And a superheated liquid is an unstable liquid that wants to evaporate due to its temperature being above its boiling point. And finally, explosive vaporization is the rapid boiling of superheated liquid, which is initiated by depressurization of surrounding gas. And to help you guys visualize this, what I have is a video that I actually took myself. And in this video, you see that there's a test tube with a liquid. And this liquid is a superheated liquid because that liquid actually wants to become a gas. It has so much energy stored up, it's actually past its boiling point and wants to become a gas. However, it cannot become a gas because there's pressure on top of that superheated liquid that prevents it from going under a boiling process. And as you can see, once the pressure is released, it causes the rapid boiling on the surface level of the superheated liquid, which is called explosive vaporization. And as the explosive vaporization occurs all the way down the test tube and room temperature makes contact with the surface level, it causes the entire test tube to go through that explosive vaporization process of the superheated liquid. And this is a picture of an evaporation wave during explosive vaporization, and the evaporation wave is actually this yellow traced line, where you can see above it there is the already evaporated gas from the superheated liquid, and below that is a superheated liquid that is still in its liquid state. And the interface is the evaporation wave, which is between the gas that's already been evaporated and the superheated liquid that is still in its liquid state. As you can see, it is a squibble. There's a whole lot of shapes and sizes that occur all throughout this video, which you might have seen on one of the previous videos I showed. And going along with that is that pressurized liquids, such as superheated liquids, are actually used in nuclear reactors as a coolant. And that's because they have heat-absorbing properties where nuclear reactors could sometimes overheat from overproduction. However, the coolant prevents that from going into like a nuclear meltdown from its malfunction. However, any damage to the cooling container can cause explosive vaporization, where if there's a crack in like the coolant container, then that will start to release the gas on top of the superheated liquid and cause the superheated liquid to go through explosive vaporization and therefore lose all the liquid inside because it's becoming a gas. So that loss of an available coolant will later lead to a possible nuclear meltdown by not having a coolant preventing overheated nuclear reactors from happening. And because of that, what I want to do is I want to learn more about superheated liquids and explosive vaporization to help combat nuclear meltdowns from occurring. In order to find a solution, the first thing that needs to be done is find out more information about the superheated liquid and their properties. And the property I decided to focus on is the velocity based on the temperature. And more specifically, my research question is, how does the velocity of an evaporation wave during explosive vaporization of a superheated liquid depend on the liquid's temperature? So what that means is that if I change the superheated liquid's temperature, how would that affect the velocity of the evaporation wave during explosive vaporization as it works its way down the test tube? And my initial hypothesis was that if the temperature of the superheated liquid increases, then the velocity of the evaporation wave during explosive vaporization will increase as a result and vice versa. The reason why I thought that is because at a warmer temperature, the molecules are already bouncing around and being more active as opposed to a colder temperature superheated liquid. And since it's already moving faster, it has less time to actually be warmed up once the pressure is released or go through that superheated liquid explosive vaporization process much quicker as opposed to the colder superheated liquid. So for my methodology, I broke my methodology down into two phases. The first phase was my experimental methodology, which is all about how I set up the experiment and actually conducted trials. And the second phase is the analysis methodology. So how did I take these trials and turn them into quantifiable data? So here is a picture of the setup I used to conduct the explosive vaporization. And in the middle, you see that there's a test tube, and that test tube is surrounded by a metal frame with a metal cylindrical disc on top of that. And above it, you'll see a metal plate attached to a piston plate structure. And what this piston does is that once air is routed through one direction, it causes this metal plate to lower onto the cylindrical tube over top of the test tube and seal off any pressure from being left out of the test tube itself. And once air is rerouted the other direction, it causes that metal plate to rise and release all that pressure. So it simulates the explosive vaporization process through the rapid depressurization. After this is sealed off, what I do is I take the refrigerant R134A and connect it to the test tube environment. And the reason why R134A is used because it actually has a very low boiling point. Its boiling point is below room temperature. So once it meets room temperature, it's going to immediately boil. So once that pressure is released, it reaches room temperature and goes through this rapid boiling process, which is what I want to simulate with this experiment. However, once the gas is placed inside the test tube and sealed off, the problem is that it's in its gaseous state and not a superheated liquid because it's not a liquid. And to take this gas and turn it into a liquid, I use a cooling bath. And this cooling bath allows me to set a specific temperature of water and cycle it through an external circulation bath and constantly maintain that consistent temperature by always refreshing it with the same temperature as what I set it to. And these temperatures range from anywhere from 0 degrees Celsius to 20 degrees Celsius, depends on what I did for the experiment. And this external circulation bath right here is completely going to be submerging the test tube, causing the gas inside to turn down into a liquid state. And over time, it's going to start to rise, but the problem is that some of the refrigerant gas that is currently in the test tube would sometimes get trapped underneath the surface level of the condensation process and cause bubble pockets to form underneath the surface. And this could actually cause impurities in the explosive vaporization process. So what I do a process called intermediate expansion. And it's done with the solenoid valve connected to the R134A refrigerant tank into the testing environment. And it opens up some of the pressure inside the test tube and causes a microboiling to form on the surface level of the superheated liquid. And over time, like a short amount of time actually, it will cause some of the surface level to evaporate and release some of the pockets that are underneath the superheated liquid. And once I believe time has passed, I'm going to seal that back off and allow condensation to continue its process of forming a liquid inside of the gaseous test tube. And after that, once I deem the test tube ready by determining it's about the right height, it's going to be about 3.5 inches. That's just the designated height I did to keep it consistent. And also it's consistently at the right temperature. I take the LED lights and turn them on, and they're attached to a metal frame I made to readjust the height to be level with the evaporation wave, the initial evaporation wave actually. And it's actually going to have cooling fans behind it to prevent it from overheating as well. And I set up my camera focusing on the initial evaporation wave, and I either do one of two things. I could either zoom in specifically on the initial evaporation wave or do the entire test tube itself and get the entire process going down. And I've done different experiments going both ways throughout my time of doing this experiment. And when I'm ready to conduct my experiment, I start the camera and I press the solenoid valve, releasing the metal plate and instigating the explosive vaporization process by releasing the pressure. And once it's all done, I take my video recording and save it all frame by frame. And I take that and I start to analyze it. And to analyze it, what I first do is I select the first and last frame of the video that I just did my experiment on. And I draw a horizontal line across the evaporation wave across its diameter. And what I'm trying to do is I'm trying to calculate the distance drop from the first frame to the last frame to find a distance. And sometimes the evaporation wave is going to be like in a squiggle. The first frame is easy because it's somewhat flat because it hasn't really gone through explosive vaporization, but earlier I showed you some of the curves that happen. So what I do when I draw my horizontal line, I draw it so about half of the evaporation wave is above and half of it is below to try to get like an average of it. So I calculate the diameter of the test tube through this horizontal distance in pixels, and I take that diameter and turn it into a ratio between real and pixel distance, so I can use that for comparison later. And then I calculate the distance between the first and last frame, y coordinates of the evaporation wave line to actually find the height dropped. After that, I convert pixel distance on the image software, and the software I used was ImageJ because it allows me to draw on top of the pictures and analyze with calculations. I convert that pixel distance into an actual real distance dropped. After that, I find the time elapsed, and that is done by taking the last frame number, subtracted by the first frame number, and adding 1. So that way you can include the first frame as well in that. And that's going to be multiplied by the FPS speed, which is the frames per second, and to find an actual time elapsed. After that, I'm going to be finding the average velocity by taking the distance divided by the time. That's going to give me an average velocity of the entire experiment. So here are some of the results that I have. This one is actually done at 0 degrees Celsius. The image on the left is the first frame of the evaporation wave, and the picture on the right is the last frame. And as you can tell, there's not so much of a distance lost, like a distance dropped. And that's because not so much of the superheated liquid actually went through the explosive vaporization process. Only a small bit of it did. And that can be compared to the 20 degrees Celsius, where the image on the left is the first frame of the evaporation wave, and at 20 degrees Celsius, and the image on the right is the last frame of the evaporation wave at 20 degrees Celsius. And as you can tell, a big portion of the superheated liquid actually went through this explosive vaporization process. And it's actually shown to the entire test tube of all the superheated liquid actually went through the explosive vaporization process. So all of it was completely released. So you could tell like the 20 degrees Celsius actually moved a whole lot faster than the 0 degrees Celsius based off these pictures. And this is also shown through the quantifiable data. And I have a graph where I calculated the average velocity versus temperature of the superheated liquid, where the x-axis is the temperature of the superheated liquid in Celsius, and the y-axis is the average velocity in millimeters per second. And as you can see based on my graph, I use a variety of different experiment temperature points, and that ranging from 0 to 20 degrees Celsius, like I stated earlier. And it's actually shown based off my experiment that I did have an exponentially increasing function, where as the temperature of the superheated liquid increases, the average velocity of the evaporation wave would increase exponentially as well. I did actually have some outliers, as you can see from the 10 degrees Celsius and the 15 degrees Celsius, but the results of my findings actually shown to be correlated highly, because it actually had a 0.7264 R squared value, so it's actually very correlated to the exponential graph. And this shows that my hypothesis was supported, where as the temperature of the superheated liquid increased, the average velocity exponentially increased as well. Initially, I did say that it was going to both increase, but I didn't know it actually increased exponentially, and that's something I found through this research. And the results reveal physical characteristics behind explosive vaporization, such as the temperature property of the superheated liquids, how the velocity evaporation wave changes when the temperature of the superheated liquid also changes. And this can be used to improve nuclear reactor designs, such as the temperature of the superheated liquids could be at a much colder state, so that way it prevents so much of the superheated liquid from leaving the test tube or being completely evaporated, so that way it gives time for people to fix the problem and maintain what's left of the superheated liquid inside of the test tube. And going further into this, I did actually have some possible sources of error, where one of them could be the evaporation waves were analyzed manually by me hand tracing these evaporation wave lines. So it could have been some human error in that. Next, that the intermediate expansion numbers were not consistent, where one experiment I might have done 2 intermediate expansions and another experiment might have done 5 intermediate expansions. And that's because I did relatively based off time, where every 5 to 10 minutes I would go through an intermediate expansion. So depending on how long it took to condense the gas inside the test tube, that would depend on how many intermediate expansions I would end up doing. And finally, the external circulation bath was removed during the videos. So whenever I was ready to shoot the video, I dropped the external circulation bath and then recorded. However, this time being exposed to the outside atmosphere could have affected the temperature inside of the superheated liquid. And going further with this research, more trials can be conducted to confirm results and give more accurate data by repetition and more data points. After that, some ways to fix some of the problems I mentioned earlier with the possible sources of error is by submerging the test tube in an external circulation bath during the actual video process to eliminate outside atmosphere temperature variables. Then after that, the videos can be analyzed in an automated system. And by doing this, it's actually able to hopefully find not just an average velocity, but a current velocity, where the velocity at the beginning of the experiment could be different than the velocity of like halfway through the experiment or at the end. So it'd be interesting to see how the velocity changes depending on what point or how long it's going through the explosive vaporization process. Now after that, finding the superheated liquid explosive temperature, like I showed you earlier, the 0 degrees Celsius, it actually had a whole lot of the superheated liquid still inside of the test tube by the very end of the experiment, as opposed to 20 degrees Celsius. So at what point is there still a whole bunch of the superheated liquid inside the test tube that it actually is not really classified as explosive vaporization because not so much has actually gone through explosive vaporization. So it'd be interesting to find that threshold temperature value. And finally, my research can be used to improve current designs of coolant containers by finding a solution and methodology to prevent the superheated liquid inside of nuclear reactors from going through this explosive vaporization process in order to prevent nuclear reactors. Finally, I do want to have some acknowledgements. I'd like to thank my mentor, Dr. Jose Grania Otero. He's been really helpful to me starting this project and giving me the materials and answering a bunch of my questions and any problems I had. He's been very encouraging the whole time. I'd also like to thank Siamak Mahmoudi and Simone Schmidt. Both of them are grad students that are working in the lab at the University of Kentucky. I'd like to thank them both for going above and beyond what they were required to do by still being there and helping me out this whole entire step of the way by answering my questions, showing me also how to run the experiments, and being there to help me out and also get into the lab. Finally, I also like to thank the Math Science and Technology Program and the Kentucky Young Researchers Program for giving me this opportunity to go out and do research at the University of Kentucky and get this awesome experience as well. And finally, I'd like to thank friends and family who have encouraged me along the way and supported me and also gave me rides to the lab. So here are my references. And finally, if you have any questions, I encourage you to email me. I attached my student email in here. So if you have any questions, I would love to hear them and I can respond back to you and hopefully answer them. And with that being said, I'd like to thank you guys for listening to my presentation. And I hope you've learned a lot about explosive vaporization and superheated liquids by my presentation. So thank you so much for listening.